So you've already learned how to recognize when an object has potential energy or kinetic energy. In this lesson, you're going to actually learn how to calculate how much potential and kinetic energy an object has. So here's our first formula. Take a moment, look at these letters, and try to predict what they stand for. What do you think this formula allows you to calculate? Hopefully you thought gravitational potential energy. We measure energy in a unit that's similar to a Newton in that it was named after somebody, but it is joules. So when you spell out the whole word, that's a lowercase j, and when you just write the symbol, it's just a capital J. So gravitational potential energy, that's the sort of energy that you have when you or some object is lifted off the ground. So let's think, what might the M stand for? And I'll give you a hint. This is the same M in Newton's second law. So hopefully you remember M is mass, and we measure mass in kilograms. I'm going to skip G for right now, and let's go to H. So again, in gravitational potential energy, what might H stand for? It is the height off the ground, and we're going to measure that in meters. Okay, now let's come back to the little g. What might G stand for in gravitational potential energy? If you're thinking something along the lines of gravity, you're on the right track, though this is not a force, so it's not actually like the strength of gravity. Instead, it's the acceleration due to gravity. So it's in meters per second squared because it's acceleration. You don't need to calculate this every time. When objects on Earth go into free fall, they accelerate at the same acceleration, which is 9.807 meters per second squared. But for this class, we're just going to always say that on Earth, gravity's acceleration is 10 meters per second squared. That's going to make the math a lot easier. So whenever you're using this formula, always replace little g with 10 meters per second squared. So I'm hoping that this formula seems like it kind of makes sense. Like what we know about gravitational potential energy is that when you lift some sort of object with mass off the ground a certain amount of height and it's experiencing gravity, then it has potential energy. So now pause your video, and in the top left box of this one-pager, I want you to write the formula that we use to calculate gravitational potential energy and tell us what the M, the G, the H stand for and what units we use to measure them. So pause your video now and fill out that box. Okay, let's get on to some examples. A car is parked at the top of a hill. Its mass is 1,200 kilograms and the hill is 10 meters high. How much gravitational potential energy does the car have? Okay, here's how we solve these problems. First of all, you need to think about what variables are important. And when I'm solving for gravitational potential energy, I need to know the mass of the object, how high it is off the ground, and what the gravitational acceleration is. Now, all of these examples are on Earth, so my g, gravitational acceleration, is always going to be 10 meters per second squared. My mass is 1,200 kilograms, and the height off the ground is 10 meters. So now that I have these values, I can actually just plug them into the formula and get my answer. So I've plugged in for mass 1,200 kilograms, for g 10 meters per second squared, for height, for h 10 meters. And now since I just multiply, I'm going to start on the left and move my way to the side. So 1,200 times 10 gets me 12,000 kilograms times meters per second squared, times 10 meters left over there. Last multiplication, 120,000 kilograms times meters squared per second squared. And this funky unit that is kind of confusing to look at, that is a joule. So my final answer would be 120,000 capital J for joule, or joules written out with a lowercase j. Now I like to keep units on my numbers as I multiply just so that I can sort of keep track if I use the wrong number in the wrong place or something like that. Like if I have meters over here instead of kilograms, I'll realize I've made an error. But if you get a little overwhelmed by multiplying all of these units, then as long as you're clear that you set it up correctly to begin with, then it's okay if you're leaving them out for now. Okay, here's a second example. Peregrine falcons have been known to fly up to 1 kilometer up in the air. When this 1 kilogram bird is soaring so high, how much gravitational potential energy does it have? So pause here and try to solve it yourself. If you get stuck, just unpause the video and you can keep pausing it as soon as you've gotten the hint you need. So in order to solve this, we need to first consider the variables we need. We need to know mass, we need to know gravitational acceleration, which on Earth is 10, and we need to know height off the ground. So the mass of this bird is 1 kilogram, g is always 10, and the height it's flying is 1 kilometer up in the air, which is actually 1,000 meters, because remember that our formula only works if we use meters for height. So here's our formula. Now I plug in the numbers, 1 kilogram for mass, 10 meters per second squared for g, and 1,000 meters for height. Now I just multiply across. 1 times 10 is 10. 10 times 1,000 is 10,000. And my unit for energy is J for joules. So finally 10,000 joules. It's kind of nuts. It's a lot of energy for a little bird. Hopefully, if there's one thing that tripped you up on this problem, it was the 1,000 meters, converting that from kilometers. Hopefully plugging it in went well. Here's another example. So pause the video and try it yourself. Unpause if you need to get a hint or you want to check your answer. The observatory, so the topmost floor that you can walk out and stand on, of the Empire State Building is 373 meters high. If a person held a 0.003 kilogram penny off the edge, how much gravitational potential energy would it have? So again, to solve this, I need to know the mass of the penny, I need to know the gravitational acceleration on Earth, and I need to know how high the penny is in meters. So the mass is 0.003 kilograms, g is always 10 meters per second squared. The height is 373 meters, and this time it is in meters, so no tricks here. So now we just plug in our numbers. Mass is 0.003 kilograms, g is 10 meters per second squared, height is 373 meters, and I multiply. 0.003 times 10 is 0.03. Bring down my 373, and when I multiply these two numbers together, I get 11.19 kilograms meters squared per second squared, or 11.19 joules. Now it is your turn. In the bottom left box, you're going to create an example problem just like what we saw. So where you set up a situation, you show a little picture of the situation with a citation, of course, and then you solve for gravitational potential energy. So in your example, make sure you include how high off the ground it is in meters, how much mass it has in kilograms, and that you're asking about gravitational potential energy. So pause the video and create your example now. So here's our second equation. Ke equals 1/2 times m times v squared. So think to yourself, what do you think Ke stands for? What do you think this formula lets us calculate? Hopefully you said kinetic energy, and we measure energy in joules. If you spell it out, it's a lowercase. If you shorten it to one letter, it's just a capital J. So if this is to calculate kinetic energy, what do you think the m and the v stand for? M is mass, and again, we're measuring it in kilograms. Kinetic energy is just mass in motion, so the v stands for velocity in meters per second. Back to your one-pager in the top right box, write in the formula that you just saw and also explain what the m, the v, and the Ke stand for. So go ahead and pause the video while you copy down this formula. Here's an example of using that formula. The car from before's emergency brake gives out. The 1,200 kilogram car starts rolling at 2 meters per second. How much kinetic energy does the car have? So to solve these problems, we need to think about the equation. It's 1/2 times mass times velocity squared. So I need the mass and I need velocity. Mass is 1,200 kilograms and velocity is 2 meters per second. So now I write out my formula and I plug in the numbers just like with the other formula. So mass is 1,200 kilograms and velocity is 2 meters per second, and don't forget that exponent. Usually when people go wrong here, it's because they're forgetting about that. Okay, so now kinetic energy is equal to 1/2 times 1,200 kilograms. And since I did the exponent first, I squared 2 to get 4 meters squared per second squared. All right, and now the only operation that's left is just multiplication. So I'm just going to go from left to right. 1/2 times 1,200 is 600 kilograms times 4 meters squared per second squared equals 2,400 kilograms meters squared per second squared, or 2,400 joules. Okay, for this example, I want you to pause the video and try to work it out for yourself. If you get stuck and need a hint, or if you finish and want to check your answer, then press play. So peregrine falcons are the fastest diving bird in the world. These 1 kilogram birds can reach speeds of 100 meters per second. When they're diving at that speed, how much kinetic energy do they have? So to solve this, we need to know the mass and the velocity. Mass is equal to 1 kilogram and velocity is 100 meters per second. So now I write out the equation, 1/2 times m times v squared, and I plug in the numbers. Mass is 1 kilogram, velocity is 100 meters per second, and I'm going to do the exponent first because that's just what you do. So I get 100 times 100 is 10,000 meters squared per second squared, and now I'm just left with multiplication, so I'm going to go from left to right. 1/2 times 1 is 1/2. 1/2 times 10,000 is 5,000 kilograms meters squared per second squared, or 5,000 joules. Another example, I want you to pause the video and try it yourself. Press play if you need a hint or if you want to check your answer. A person drops a 0.003 kilogram penny off the Empire State Building, and its velocity is 11 meters per second on the way down. How much kinetic energy does the penny have? By the way, in the article where I got this picture, it says that 11 meters per second is the terminal velocity of a penny. Who knew? Okay, so to solve for kinetic energy, again, we need mass and we need velocity. Mass is 0.003 kilograms and velocity is 11 meters per second. So now you write out the equation and plug in mass and velocity. So Ke equals 1/2 times 0.003 kilograms times 11 meters per second, and that velocity is squared. So I'm going to do the exponent first. 11 times 11 is 121. And now just bring down the 1/2 and the 0.003. 1/2 times 0.003 is 0.0015 kilograms. Bring down the 121, and 0.0015 times 121 is 0.1815 kilograms meters squared per second squared, or 0.1815 joules. So this article was all about how it is a myth that dropping a penny off the Empire State Building could kill someone. And now that we've calculated how much kinetic energy it would have at its terminal velocity, we can see why. It's really not that much energy falling and hitting you. Way less than the peregrine falcon. Back to the PEKE one-pager, bottom right-hand box, you're almost finished. Create another example problem where you give us the mass and the velocity, and you ask us to solve for kinetic energy.